You wrestled with that bad number 10 problem last night, eh?
Oh, I did.
And you got it.
I got it.
Yeah.
Took a while.
That's a tough problem, so that's good. And like working on those hard problems, it's surprising, but it really does help.
Yeah, it makes the easier ones a lot easier.
Yeah, that's right. Yes, actually, the best way to learn checkers is to get good at chess. And what?
No, that makes sense. That makes sense.
Yeah,
it makes the
easier ones a
lot easier.
Yeah, that's right. Yes, actually, the best way to learn checkers is. I don't know what's happening there. Oh, okay, that might be like going through Jeff's speakers or something like that.
Here, hold on. Turn my volume down a little.
All right.
All right, there we go.
Okay. So you did the preamble about like me trying to sell webinar tickets. If you get a chance, actually go to the Perimeter Institute. It's can be a very interesting lecture, but it's a kind of a nifty place as well. But they do give away tickets to lectures, and we've gone a few times, sort of taken a school trip. And probably we would pay for it, but it seems like they've got a better idea than that.
Oh, that makes sense.
So, okay, here we go. So we're going to look at one of these problems. Once again, this is one of those issues where you change one variable and it changes another, and ultimately things are going to get optimized. So in this case, we have a 2,000 passenger train. We're charging $7 a ticket. Every time we increase the price by 10 cents, we are going to get 40 fewer riders. Webinar tickets. Happens if we decrease it. Chance, actually go to the Perimeter Institute. I know what it's a very interesting lecture. I can actually get rid of my volume. There we go. Oh, now we can't hear Jeff.
Okay, I messed up.
That's all right.
I fixed it. Okay, it's all good.
Oh, what was going on?
Okay, so I had the course open in another tab, and the live stream was actually playing from the YouTube host on that. So I was hearing everything about 10 seconds delayed. So it was just confused. All right, it's all good.
Yeah. Okay. Well, I was kind of wondering about that, but sometimes it isn't that. Sometimes people will like come into a Hangout and there'll be a sort of an ongoing echo. So that's good. Anyway, we're going to try and maximize revenue. We aren't going to worry about profit, at least not right now. And so revenue is the number of tickets times the price. And what we're going to say is X is going to represent the number of 10-cent increases. Oh, boy. There we go. So X is going to be the number of 10-cent increases. And so we're starting out with 2,000 people riding our train. And for every X increases, we're going to lose 40 of them. So there's the relationship that we have for the number of people that are going to be riding the train. And we are going to multiply that by price. And so we're starting out at $7. And every increase is going to be 10 cents. Okay, so there's the number of riders. And there is there's the price that we're going to experiment with. And you can see, actually, this is fairly important. Okay. What do I have there?
The price?
I don't have it 10 cents for every X.
There we go.
0x. We'd wind up with a wacky price, a pricing system that way. Okay. Are we at the stage where we can take the derivative yet?
Not quite.
No. Well, I guess we could take the derivative. We could use the product rule. But let's expand this out just because I think that's going to be a little bit easier. So 2,000 times 7 is 14,000. Wow, I can do that in my head. 2,000 times 0.1. This is going to be 200. X 40 times 7, that would normally be, that is 280x. And then, oh, here comes the x squared term, bringing up the rear. This is minus 4x squared. And so I wind up with minus 4x squared minus 80x plus 14,000. And so this is my revenue function. And just like always, I want to make the most money. That's not entirely true. When I say it that way, that makes me sound really selfish. But in this case, we're going to go for the highest revenue. Okay. What should we do now? Let the record indicate that Lindsay is saying take the derivative. Okay. So dr dx, the change in revenue with the change in the number of price increases, is going to be negative 8x minus 80. That's it. And what we're going to do, set it equal to 0 so that we can find any max and mins. Negative 8x minus 80 is equal to 0. Move the 80 over onto the other side, divide it by negative 8. And it turns out we should actually lower our price.
So that means you'd lower it by $1 then?
Yes, that's right. So we would go with taking away 10 of those 10-cent increases, basically. And so it turns out that we can get more riders on if we lower our price by $1. A lot more people are going to ride. So that kind of makes sense.
Yep.
Okay. You could say you should charge $6. So not surprisingly. So economists spend a lot of time, and actually this is something that like a systems analyst or something like that might do, trying to find out what the optimum price is. But maybe we should figure out how many people actually would be riding the train at that, because let's say we can only get 2,600 people on our train. Let's find out if this is going to work.
I see.
So we know how many people. We actually have a function for the number of people here. So n is equal to 2,000 minus x times 40. And so 2,000 minus negative 10 times 40. So we would get 2,400 people on the train for that. If our train held 2,600, we'd be good. We could lower the price, we could increase the ridership, and we're going to increase our revenue. Usually on something like a train, the big money is involved in like putting it on the track and hiring the people. Anything that you get at that's extra doesn't really contribute that much to the cost. Like if you're pulling a train of 2,400 people, it probably costs about the same thing as pulling a train of 2,000. Mm-hmm. So increasing the price probably doesn't increase the cost. So this is probably the way to go. And if we were asked for the revenue, we'd just plug that x back into our original function. All right, that's that.
Nice.
Yeah, pretty easy. I should go over that question that Jeff wrestled with last night. That's actually, that would be considered quite a challenging question.
Yeah, that was.
And we'll put it out there for people to look at. And so just so you know, I think this kind of question, I don't know if I've ever had too many students who could have like done this question just by looking at it, because there's a lot of elements to it that are very tricky. And then that final element where you're where you try and minimize the distance squared, That is like a dirty trick that you almost have to be told that this is the easiest way to do this problem.
Yeah.
Okay, so we have a parabola, and the parabola has the equation y equals 9 minus x squared. And so, yes, it's upside down. Y-intercept is 9. X-intercept is 3. And what we were actually asked to do is minimize the difference between the 0.39 and the parabola. And so a sketch is the thing that, I don't know, a sketch always helps. Helps you visualize the problem. And this distance here is what we are trying to minimize. And so from grade 10, there was this crazy distance formula. Distance on the plane. And it actually seemed like it was, you know, more complicated than it needed to be. Instead of just telling everybody, you know, just do the Pythagorean theorem. You gave out this formula with all these subscripts. When we were in physics, we were doing, we're starting to do those collision problems. And there's actually quite, there are parts in the problems, at least in the textbook, where there are 3 subscripts on every variable.
Yeah.
So it's pretty, yeah, it can be pretty,
A little messy.
subscripting and just processing all that stuff can be pretty onerous.
Mhm.
So this distance is actually what we are trying to minimize. So this optimize, I'll put this here. We have 2 variables in this expression that we're trying to optimize, an x and a y. And what we're going to do is we're going to use the fact that x and y are related by the expression 9 minus x squared. So this is what we're going to use to relate our variables together. And we're going to substitute back into the original expression. There's a little bit more information I can fill in my distance equation, though, because I know my x2 and my y2, 3 minus x, my x2 is 3, 9 is my y. And so I can actually express this distance relationship in this way. If I look at the equation I'm going to use to relate the 2 variables, y equals 9 minus x squared, this one is ready-made for substitution. And so I'm going to take the y, which is 9 minus x squared, and I'm going to substitute my 9 minus x squared down here. Nine minus 9, and then this winds up being plus x squared. Good so far?
Yep.
Haven't done anything wrong yet? I mean, haven't done anything wrong on purpose yet? We'll do a little bit of simplification here. 9 minus x squared. Squared. Is that right? Is that the way that ends up? Oh, yeah, it does too. Okay. X to the 4th.
Yep.
Okay. This is what I was telling Jeff. This is where there is a dirty trick involved in actually finding the minimum of this d equals this square root thing. This is going to be a horrible expression to deal with if we use the chain rule. Actually, I never thought of it. Maybe I should have tried it just to see what it looked like. But minimizing d is actually the same as minimizing d squared. And so we can square both sides of this, and we'll still have an expression that we can find the minimum of, but it's just going to be d squared, which will happen for the same value of x.
Mm-hmm.
So d squared is equal to 3 minus x squared plus x to the 4th. I guess I should have simplified this first. 9 minus 6x plus x squared plus x to the 4th. Okay.
Yeah, that's what I had.
So it's calculus. We want to find the minimum. What should we do? Let the record indicate that Lindsay has mouthed the expression, take the derivative. Okay. You can just ignore what I did over here. It's called implicit differentiation. Ho, don't look too terrified. We don't have to worry about that too much, but we will, we'll just do the right-hand side here. 4x cubed plus 2x minus 6, and I can common factor out a 2. Oh, yeah, there we go. Have I done anything wrong? I've done something wrong, haven't I?
X. Oh wait.
Oh yeah, here we go.
Yeah, there we go.
There we go, and this should be an X. Okay, very good. I just don't know how to common factor, that's all. So we're going to set this equal to 0 to find our critical points. Cubic equation. What are we going to do to try and figure out the factors of the cubic equation? So we can just use the factor theorem?
Yeah.
Okay, and I can see, I'm going to look for factors of -3. I'm going to try a 1 in here. And so 0 equals 2 times 1 plus 1 minus 3. X equals 1 is a 0, and that means that x minus 1 is a factor. Okay, and so we might as well just factor this out. Sorry, Jeff, you probably did this all last night.
Yeah, I did my best. It's good to watch it be done too, though, I find.
Is it coming off any differently than the way you did it?
No, it makes more sense now. Like it's more solidified.
All right. Okay. So I know I need a 2x cubed in here. So that means I need a 2x squared here. That means that right here has to go a minus 2x squared because I'll be multiplying 2x squared by -1. I don't have any x squared terms, so I must have a 2x. I must have a plus 2x squared right here so that those cancel out. X times something is 2x squared, and so there's a 2x goes here. This is minus 2x, but I need a plus x, and so I'm going to have to get plus 3x in here. If this is a plus 3x, I need plus 3 here. That's going to make a minus 3 here. I don't have any remainder, and so I've done everything right. I can actually factor that into this. And so I've factored it down into this binomial and this quadratic. I might want to check this quadratic to see if there are any additional zeros, see if there are any factors. And so it doesn't look like it's going to factor. Before I go that route of like trying out the quadratic formula though, I'm going to see if the discriminant is greater than 0. So I'll know if this has actually got any zeros in it. So b squared minus 4ac has to be greater than 0 for this thing to actually do that. And so b squared is 4 minus 4 times 2 times 3. And that's going to be less than 0. 4 minus, what is that, 24?
Yeah.
It's less than 0. So there are no roots in the quadratic. X minus 1 is the only factor. And so this thing reaches an extreme value when x is positive 1. All right, if I went back to the go back to the original diagram. There's my original. And so the closest point of approach is actually going to be at 1 and 8. Right there. And I could probably work out this is 2 and that's 1. This is going to be like the square root of 5. Okay, that is a challenging problem.
Yeah.
So all I'm going to do is, Lindsay's giving it the quizzical cat look right now. Oh, and the I've got a headache look. Anyway, any extra questions, Jeff?
Not about this or any of that. I had a question about the graphing, like if we were graphing like full analysis sort of a graph of a function.
Yes.
You know how we do those like charts for like when you found roots for the like I don't know, what do we call those charts where we check the
interval table.
Yeah, interval tables.
Yes.
I was just doing a couple practice polynomial graphs, and like, are those? Do we need to do those? Like, I mean, like we definitely should, but like, are they? Do you need to do them to solve the question? Like, are they required?
No. So somebody actually emailed me about that. They said, I haven't seen the tables before.
Yeah.
Can I just do it? The answer is absolutely. You can just go ahead and you can solve it like in any way that you prefer.
Okay.
You don't have to use an interval table.
Like, it's good to check, I find. Like, it's good to make sure you're on track with it.
Yeah. But if it doesn't suit you, don't feel obliged to use an interval table.
Okay.
There's nothing that's required about it.
Okay.
I really like it personally.
Yeah.
It just, you know, you can see from the table how it works out on the graph. You can see each of the points. You can see how the factors multiply together to, you know, make your positive or negative intervals in either the original function or the first derivative or the second derivative.
Mm-hmm.
But they are not required
Okay.
for you to do any of the graphing.
Okay.
Yeah. So if you're just saying in this interval it's negative, and you know that means, you know, below the x-axis.
Yeah, exactly.
Negative slope, or, you know, concave down.
Yeah.
That's all you have to do. So you definitely don't have to do it as an interval table.
Righty.
Yeah.
I mean, they work. They make sense too. So I was just wondering, because I was working through the problem, and like I didn't really need it to visualize the graph at first. Like I was kind of like, okay, well, I like if it's like a third degree function and it's positive, then you know it's going to increase from the left to right. So you don't really need to do an interval table for the original function. Like
That's right.
how I would work through it.
Yeah, yeah. No, they're not required, and it's like you're saying. Yeah, sometimes you can surmise what's going on. Like you don't really have to. You might not need an interval table.
It's good to know.
Give me, even like a 2 or 3 word indication, of what your thinking is.
How I knew. Okay, yeah.
Yeah, yeah.
Okay. Sounds good. Yeah, that's all I had.
All right. Yeah. Okay. So this is pretty light. I think I'm going to put up like 2 questions. They're not the CEMC questions. I'm just going to put up two questions to do, and then we can study for curve sketching. What day is it today? Oh, okay. So tomorrow I am actually going to start into the next unit, just because the first part of the next unit, A, it's interesting, and B, it's easy. So we'll do that tomorrow, and then Thursday just will be review for curve sketching, and then Friday we'll do the test.
Okay. So for the optimization problem on the test, are we going to be or is it going to be more of an economics optimization, or is it going to be like more so what we did yesterday?
I'll tell you what. What if I told you I kind of thought maybe I won't put an optimization problem on, and we tack it on to the next test, or would you rather have it this test?
I don't know. If we're gonna do it anyways,
Do it now.
May as well just. That's my opinion.
Okay. Lindsay seems indifferent at this point. I'll tell you what. We will do it now because it is a little bit related to curve sketching, and it gets it out of the way.
And it's pretty fresh, I think, right now.
Yes. Yeah. And then our next test, I think we just basically work through next week, and then we have our last calculus test. So our last before we start into vectors. So
yeah.
Tomorrow's the equinox. Actually, we're halfway through the course.
Nice. Okay.
All right. Okay. Thanks, Jeff.
Yeah. Thanks for having me again.
See you tomorrow.
Yep. See you.